Hello, my name is Scott Liorna. I'm a PhD graduate student with the University of Alaska Fairbanks, and today I'll be presenting a talk titled Estimating Animal Size and Distance in Camera Trap Images, Photogrammetry Using the Pinhole Camera Model. So I'd like to start with an example from my own research in using camera traps to monitor caribou in Arctic Alaska, where we wanted to answer these two questions. How could we determine the distance to animals in these images, and how could we measure their sizes? And these answers to these two questions have a lot of implications and can lead to enhancing the type of data that we can collect beyond just presence and absence of animals in our cameras. And so answering these questions is really what motivated this talk and the stuff that I'll present today. So the first methods that we came across in the camera trapping literature for estimating the distance to animals in images simply used reference objects placed at known distances and then compared those to the position of animals in the image to assign them to a distance interval. And other methods reviewed the images in the field and then recreated the position of animals and simply just measured the distance from the camera to where they saw the animals in the image and recorded the angle to estimate the area sampled. And other methods like the one to the right here, where they actually essentially calibrated each site's field of view using a grid of known dimensions and then superimposed images of wildlife on that grid to determine their distance and angle. But these methods weren't a great fit for our task because our images were already collected and our sampling sites are extremely remote and difficult to access. So we couldn't really go back out and take these measurements in the field. And current methods described for estimating animal size essentially use a reference object of known dimensions that's located at the same position of the animal to scale the image and measure different dimensions. And then finally, this last approach, which is known as stereo vision, which uses multiple cameras positioned to take an image of wildlife from two different perspectives simultaneously, and then the relationship between those cameras and the image of the animal in the image is used to calculate size or distance. But again, these methods weren't applicable to us since our images had already been collected. And so to review some of the limitations and challenges of current methods for estimating animal size or distance to the camera, the first is that if physical reference objects are placed in the field of view of the camera, these can attract or deter some animals, and also if the field of view of the camera has to be calibrated at each sampling site, this may lead to increased disturbance of the habitat directly in front of the camera through trampling of vegetation or spreading human scent in the area, which again may change animal behavior or use in front of the camera at that site. Also, any shifts in the camera position may lead to increased errors in estimates or the need for recalibration, which might be caused by leaning posts or animals pushing them over or messing with the cameras. Also, pre-processing of images is necessary if you intend on recreating the position of animals based on their location relative to some landmarks in the image, and this can increase the amount of time spent in the field. Also, some of these methods don't lend themselves to estimating continuous distance or size, such as the examples of assigning animals to some distance interval between two known distance markers. And finally, stereo vision methods can be quite difficult to implement with the increased complexity requiring multiple cameras, which inevitably leads to increased costs, labor, and storage. And so we didn't find any method in the camera trapping literature which would satisfy our needs and be relatively easy and simple to implement. So we searched more into the computer vision and more broad image analysis fields and came across a conceptual model known as the pinhole camera model, which seemed promising. So we developed a study to figure out whether this method could help address some of the current shortcomings or limitations of current methods described in the camera trapping literature and whether it would be better suited to our task. So first, a little bit of background on what the pinhole camera model is. And it's essentially a conceptual simplification of a camera with a lens, but instead of a lens, it condenses that down to a single point. And the relationships between the physical world and what's going on in the camera can be summarized by similar triangles. And based on those relationships, the following equations can be derived to estimate the size of the object in the physical scene, or the distance between the object and the camera, which is ultimately what we were interested in. Or they can be rearranged to estimate the specifications on the camera side of things as long as 3 out of the 4 inputs are known. And while the size of the object on the image can be easily measured in pixels using almost any image processing software, Most camera trap manufacturers do not report physical specifications of the cameras, such as the focal length. So our first step was to try to derive the focal length in pixels, and this process is often referred to as camera calibration, when the goal is to derive some attribute of the actual camera. And so to do this, we essentially did our best to control for the remaining three parameters, which included the physical size of the object, which we simply used a piece of paper of known dimensions on poster board, the distance to the object, which we measured carefully, and the size of the object in the image, which we measured using the open source software ImageJ. And to see whether this calibration procedure worked for different cameras and with different settings, we used a lower cost Campark T20 camera, which can be found on Amazon for around $40, and the cameras that we were actually currently using in our Caribou study, which are Reconyx Hyperfire 2s, and they can be found for about $400 a piece. And we chose two different image settings related to image resolution for each camera. And we carried out this calibration procedure with three cameras of the same make, model, and image setting, and we found that this calibration procedure led to very precise estimates of focal lengths, and that they didn't differ between similar cameras, meaning that we could safely apply these derived focal lengths to all cameras used in our study. And so with this information, the next step was to try to apply this method to actually estimate the physical size and distance to things in the image. So to do this, we first started in a controlled setting where we could really understand how well this method would perform under ideal situations. And so we took our cameras out to a local archery range and recorded images of three-dimensional animal targets up to 25 meters away, attempting to capture them near the center of the image and perpendicular to the camera. We measured their shoulder height and nose to tail length and the distance to them, which we later used to estimate the size and distance based on the pinhole camera equations. And we found that this method resulted in highly accurate and precise estimates, with size estimates underestimated by about 3% of the actual size of the target, and distance estimates overestimated by about 3.3% of the actual distance. And we use relative error as a standardized measure of accuracy, which is simply the standardized difference between the actual and estimated size or distance. And we felt that this was a good measure that could be applied across a range of applications and give the most generalizable results. And in the simulation, we also found that there were no statistical differences between the mean relative error between image settings within camera models, between the two camera models that we test, or between the measured dimensions we used in calculations, which again, for this were the shoulder height and the nose to tail length. So we were really excited that this method seemed to work really well in a controlled setting, but we also wanted to know how well it would work under more realistic field conditions. So we applied the pinhole method approach to captive reindeer at the Large Animal Research Station at the University of Alaska Fairbanks to try to assess how well this method worked in a more realistic field setting. So for this assessment, we did not attempt to capture reindeer in any particular location in the image or in any particular angle to try to best replicate what might be expected in a camera trap application where animals are moving in front of the camera in an uncontrolled way. And for this, we measured several morphological dimensions of reindeer, including their shoulder height, foreleg length, back length, hind foot length, and their total nose to tail length, and recorded their distance when the image was taken using a rangefinder, which we varied between anywhere between 5 meters and 100 meters away. And we found that there were only slight increases in relative error of size estimates and distance estimates compared to our controlled simulation, with size estimates on average being underestimated by about 8.6% and distance estimates being overestimated by about 10.5%. And this was more or less expected to some degree since we were working in a less controlled environment, and there was likely more measurement error on our part across the board, which overall we were really satisfied with this outcome. I do want to point out here that these error estimates would be representative to a scenario where you might have morphological dimensions of known individuals who are captured right next or near to an object of known distance. Otherwise, these errors are likely to increase as the variation and uncertainty in these factors increases. And in the next slide, we'll go over how we can theoretically determine just by how much these factors are likely to increase errors and estimates in maybe more or less controlled systems. Which brings us to a discussion on the limitations of the pinhole camera model, which these include errors in the known or assumed parameter inputs, or variation in the orientation of the measured morphological dimensions relative to the camera, which are known as perspective distortions. And if these are left unaccounted for, these can really influence the outcomes. But as we showed in our simulation, if you do account for these carefully, the method can still provide extremely accurate and precise estimates. And the next two are optical distortions, which are an artifact of curved lenses using camera traps and is not accounted for in the simplified pinhole camera model. And the last is that this model requires that either the size or distance is known to estimate the other, which is not a limitation of many of the other methods. Which leads us to offering a few things to consider if you end up using this method one day to get the most out of it and attempt to minimize potential sources of error. And while there is no one-size-fits-all method for almost anything in field studies, there are a few things that we suggest users of the pinhole camera model to be at least aware of when applying this approach. And these include using morphological dimensions with low variation among individuals. For example, if hind leg length for some species had less variation than its total body length, then this would be preferred if it were available. To remember that the orientation of any measured dimension relative to the camera can affect estimates, particularly when they're severely skewed. So when this is the case, having alternative dimensions available can be helpful. For example, if the animal is quartering away, attempting to estimate its nose to tail length without accounting for its reduced apparent size in the image would lead to high errors in estimates. However, its shoulder height would remain relatively unchanged. So just being aware of this is something that's important when you're applying this approach. If you intend to use this method for estimating sizes, think carefully about how you can attempt to control for where animals are likely to be captured in the images, and possibly attempt to select your sampling locations to control for this. And if this is not possible, we suggest removal methods like the ones described earlier of reference objects to avoid any researcher-induced changes in animal behavior. And if and when you can, to minimize any potential errors arising from optical distortions, what you can do is just try to use images where animals are centered in the image, which obviously is not going to be the case for every image, and like we mentioned before, is probably not a big issue for most of the camera trap models on the market. And then finally, obviously, the better the quality of the image, the more accurate and precise your measurements of pixels will be. So don't be fooled by the marketing hype regarding megapixels. Some camera trap manufacturers increase the pixel count using a process known as pixel interpolation, which essentially just subdivides the native pixels into smaller and smaller units while not actually increasing the clarity of the image. And we are unaware of any study documenting which manufacturers do this, but we suspect that the Campart cameras that we used did this because they reported a pixel count of 16 megapixels compared to the 3 megapixels of the Reconex, but the Reconex images were much clearer than the Campart. So just being aware of this and maybe not falling for manufacturing kind of sales pitches is something to be considered. So just to summarize our experience with using and evaluating the pinhole camera model in a wildlife camera trapping context, we feel it offers solutions to many of the previously identified limitations of current methods while remaining conceptually simple and really easy to implement. And we feel like as long as you put good data in, you'll get good results out, as we showed with our simulation data, which only had about 3% relative error for distances or sizes. And being aware of the pinhole camera model limitations and other suggestions that we provided for minimizing error will maximize its utility when you apply it. And the pinhole camera model did what really no other method was able to do for us specifically, because we were trying to apply some method retrospectively with images that we had already collected to determine the distance to animals. And so this method really filled that hole for us. And our intent is to use morphometrics reported on caribou to estimate the areas effectively sampled across our network to help account for observed variation in capture rates among sites. And we may also in the future explore whether it can be used to estimate movement rates, monitor changes in body condition through different important life history stages, or to track growth rates throughout the season. So stay tuned for more on that. And ultimately, we recognize that no method is likely to satisfy every project's needs, and a combination of methods may capitalize on each method's inherent strengths while resulting in more accurate and robust estimates than if only one approach was used in isolation. So thanks again for staying and listening to the talk, and I hope you found it educational. and useful for any future projects that you might do. And I'm happy to answer any questions that you have. Thank you.